Yeah, I'm Remco Groenenberg, the lead scientist of the HyUSPRe project. And thank you for the invitation to present some of the results of this project that actually ran for 2 years and 9 months and finished last June. It was funded out of the 2020 call of the, well, let's call it the Clean Hydrogen Partnership. So that's Horizon Europe funding. And it was the second project to be granted from this call. The first one was actually the HyStories project, and I think the next presentation by Ceri will be about some of the results of that project, right? So, but that's a bit the link. We are in a way sister projects, whereby the HyStories project was started 1 year earlier than our project. So this is why HyStories has been ended for a while already. Yeah, so the HyUSPRe consortium, very briefly, we were a consortium of 17 partners, of which 10 from industry, 4 research institutes, and 3 universities in total. And yeah, and from the industry partners, you recognize, I'm sure, a lot of gas storage operators and oil and gas companies, and also some, at least one TSO, transmission system operator, some from Italy. I think actually Markus Pichler from RAK will present the third speaker. So RAK was also one of the partners in this project, and yeah, we're actually very grateful for their contributions, both in knowledge and experience, but also in sample material, for instance, that they provided us with to conduct the experiments that we did among others, and in general just for guidance. Yeah, on the research institutes, you recognize TNO. TNO was the project coordinator of the HyUSPRe project, and for the rest, we had EGS GEEG from Austria, Fondazione Bruno Kessler from Italy, and Julie from Germany. Forschungszentrum Julie from Germany in the consortium, and from the university side, the University of Edinburgh, Clausthal, and Wageningen, all well known, and of course funded by the Clean Hydrogen Partnership. I mentioned that. Yeah, so this is a diagram that shows the HyUSPRe objectives and the research program that we conducted. So yeah, a 2.5-year project, quite a lot of research was done to actually also be able to to fulfill the requirements of the call text initially, of course. And yeah, roughly it can be divided into 3. There was a first work package more on assessment of hydrogen storage potential in porous reservoirs in Europe, mapping locations in relation to production and demand sides and transport infrastructure. I have a few slides on that. And then there's 4 work packages, more experimental work, geochemistry, microbiology, flow behavior, integrity, and durability. I have a slide on each with highlights of results. On 6 and 7, I don't have a slide. I mean, 15 minutes is just too short to completely go through the results of this project entirely. But I will point you at the website from which the HyUSPRe website, from which all the results, deliverables can be downloaded. I think there's about 50 plus in total. I do want to highlight, though, the roadmap for successful deployment of underground hydrogen storage in porous reservoirs in Europe, which was actually the final deliverable. And where we basically summarized not just the outcomes, but also painted a picture on how underground hydrogen storage in porous reservoirs could be successfully deployed and what would be needed in terms of actions to achieve that. So yeah, so this is this was basically the work that we did. Yeah, a bit more on storage, hydrogen storage. Why do we need that? Well, I'm not going too much detail on that, but there was work done by Forschungszentrum Julie on this. It's clear that hydrogen storage as well as hydrogen, of course, can be key enablers to unlock the benefits of hydrogen, both on the side of decarbonizing hard-to-abate end users, and also in terms of enabling renewables penetration, distribution, and system resilience. On the industry side, for instance, it offers flexibility to balance supply and demand and build value chains. It enables optimization of infrastructure sizing and balancing of flowing pipelines on the infrastructure side more. And in an early stage of the emerging hydrogen value chain and hydrogen economy, it can really help to support the kick-starting of that hydrogen economy while the infrastructure for transport is built. So basically security of supply. And then more from the system perspective, The left more from the use or demand perspective, and on the right more the system perspective. It offers flexibility to maximize renewables integration and reduce curtailment by converting, always having a way out for electrons to convert it to hydrogen, increasing system robustness and resilience, and improve energy security and increases independence. Is also clear by enabling long duration energy storage and maintaining strategic reserves. So that's more a bit on the role of storage in the future energy system. And then Forschungszentrum Jülich, through a combination of desktop study and modeling with energy system models, looked at.
It's almost 10 years now. Starting with the underground sun storage project, which is actually, or was the first project where RAG touched in the field upon the storage of hydrogen. At that time, it was still the question of, could we safely store a mixture of hydrogen and natural gas in the subsurface? And so at that point, we just had a injection of 10% of hydrogen with 90% of natural gas, but it was a very successful project, and we could prove that we could safely store hydrogen together with natural gas in a depleted gas field. So it was a depleted gas field at that point, a small one to be fair, but it still was. And therefore we said, okay, that's a positive result. So we should actually go further and see if we could, on the one hand, do higher shares of hydrogen in the subsurface, and on the other hand, what else could we do? And this is why, first of all, the next project that was born was the underground sun conversion project. And this project actually did not focus on the storage of pure hydrogen, but focused on the storage of hydrogen together with CO2 because, and that many of you might know, that there are microbes in the subsurface that do naturally convert hydrogen together with CO2 to CH4. And so our thought was of utilizing this process and trying to establish it on an industrial scale. Furthermore, we also participated in several research projects that you all can also see here on my screen, namely the most and foremost the European projects HyStories and HyUSPRe, which will be both introduced today, so I don't have to talk about these. And I also won't go into detail about all these other projects that we did. Suffice to say that we looked at the whole value chain of hydrogen storage that is possible, both from a technical as well as from an economic and a legal perspective. And as I only have 15 minutes, I can't go into much detail there. But afterwards, if there are any concrete questions to some of these projects, I would be happy to answer them. Today, I'll solely focus on hydrogen storage. What is the Underground Sun Storage 2030 project all about? Basically, as I said, we want to prove that the storage of 100% of hydrogen in a depleted oil and gas and in a depleted gas reservoir, in a depleted porous gas reservoir, more precisely, is an option or a solution for interseasonal energy storage. I don't need to tell you the story about the fluctuating renewables. You all know them. I don't need to tell you the story about why hydrogen. It's obvious. So I just want to focus now on the hard facts of what this project is all about and what on preparation went into this project, and finally what we got out as the first results. So what will we prove? We proved the technical feasibility of hydrogen storage. What is very important for us within this project is that we can compare the results, the really tons of results. We're speaking of 10 years worth of laboratory research with an actual field case where we can either falsify or verify these results that we got from the laboratory, and if they're falsified, then say, okay, what is the difference? Why did we see in the laboratory something different than we see now in the field? As well as focusing on all those special points that we haven't touched upon in the last projects, being, for example, the demonstration of the hydrogen purification, which is very important. You know, all of us, if we have to supply hydrogen or energy in whatever way to some end users. They want to know beforehand what they get, and there is this thing of hydrogen mixing with the other gases in the reservoir. So that is an actual very interesting question, whether or not we can provide a constant quality of hydrogen, or if there is a problem. So purification is very important, and this project is still on the Austrian scale, so we're more looking on an Austrian use case, but will then be extended in a follow-up project. I will shortly talk about that, to a European scale. Last but not least, what is also an important part of this project is the whole topic of public acceptance, because we all know we're talking about huge infrastructure projects, and there are many huge infrastructure projects never being built just because they didn't have the public support and therefore didn't get all the permits that were needed to establish them. So here the two pictures which might also give you a hint why public acceptance is so important for us. The actual place where the hydrogen storage takes place is in a very scenic countryside near the Lake Attersee in Upper Austria. So people there are rather sensitive about the environment as well as about the landscape. And if you build them some ugly facilities into the beautiful landscape, then they don't like it because of the touristic interests that they have. So we were talking about laboratory preparation. So let's go and take a deep dive into technical details. I'm a reservoir engineer, I said that already, so we're mostly focusing today on subsurface details. If you have any questions to surface details, to material sciences, and so on, I might have an idea, but if not, then I'll take those questions with me and just answer them later. Let's start with geochemistry. So we all know hydrogen is a highly reactive molecule, and on the surface there are a lot of reactions that we're actually aware of that could happen if hydrogen is present. So the first question that needs answering is, if we inject 100% of hydrogen into the subsurface, is it the same? Do we have issues there? Is there a problem with hydrogen reacting with any of the substances that we find in the subsurface? And therefore we did exposure tests with material actually from not from the reservoir, but from the same geological environment. So it's a Haller series environment, and we had no material from the well itself, but from a well that is close by and has the same properties. We did these exposure tests in a wet environment under reservoir conditions for 1 year. You can see that here, and fortunately saw no changes, which is a very positive result for us. And we can also further verify this result with the fact that we have, as I told you, had research on hydrogen storage for the last 10 years, just with hydrogen mixtures. But still, if there would have been any reactions that would alter the reservoir properties, we should have seen them by now, and we didn't see them in the reservoir. So we can conclude that at least for our setting, for our temperature, pressure, and reservoir setting, we should be safe by storing pure hydrogen in the subsurface. Apart from the geochemical reactions that might happen with the reservoir rock, there is also the stability of the cap rock, which is very important because this is the whole integrity story that we're here talking about. So we want the cap rock to contain our hydrogen and not let it escape to the surface or to any other adjacent layers. And in order to do that and to be sure that our cap rock can contain the hydrogen, we again took samples. Again, not from this well, but from another well also in the vicinity, the same where we got the reservoir rock from, which is also in the same geological setting. It was important for us to have fresh cores. So the cores were cut or were drilled only half a year before this project started. So they were in rather good condition. They were also stored, wrapped in foil. So without any exposure to oxygen, without also any exposure to changing environments under constant temperatures. And so we tested, first of all, the migration speed of hydrogen in the cap rock and found that it is comparable to methane, so very, very low. And Secondly, what was even more positive for us was that we found in the experiments that the entry pressure that hydrogen needs to enter the pores of the caprock is even higher than for methane if it is a water saturated caprock. This has to do with the interfacial tension between the hydrogen molecules and the water molecules, which helps us in a way that the hydrogen has an even harder way entering the caprock. From this, we could actually conclude and say, okay, it doesn't enter the caprock, so I don't care if it does something with the caprock. We didn't do that. Obviously, we wanted to prove that the caprock is safe. Therefore, we also tested for chemical alteration of the caprock. There was none to be found. And we're currently also testing if the caprock or if the mechanical properties of the caprock might be changed due to the exposure to hydrogen. Until now, we haven't really seen any changes, but as I said, these experiments are ongoing. A very important point, and I apologize, there is very much writing on this slide, but this is more or less summing up 8 years of research in one slide. That is a bit difficult, but I try. And there was this important question, what the hell do the microbes do with hydrogen? Hydrogen is very good for many of the microbes in the subsurface, being it methanogens, being it acetonogens, being it the famous SRBs. So all of those microbes could possibly utilize the hydrogen if you inject it into the subsurface. And we had this underground sun conversion project I was talking about, where we actually wanted to utilize the process of CO2 and hydrogen together being converted to CH4. And that works, but not in a way that it would be economically feasible, but still the project was insofar a success as that we learned a lot about metabolization rates of microbes in the subsurface and how they react on the injection of different gases in different gas compositions. And what we found, and I think that is the key message, is that as soon as there is no longer any gaseous CO2 available, the microbes stop metabolizing, which is a very positive message actually for us, because now I can say if I inject pure hydrogen, I shouldn't run into any issues. There are still two open questions, one being whether the microbes could use the calcite and dolomite in the reservoir in order to also generate CH4 because they have a new carbon source. We haven't found any information in this regard yet, but we're still doing research on that. And also the H2S generation. We see H2S generation in one of the reservoirs, in the one where we did the microbial tests, but only very, like, I would say heightened background. So we're speaking about 1 to maybe 3 parts per million share of H2S in the withdrawn gas, which is actually just because there is some sulfur, so SO4, in the reservoir brine, and this gets converted to H2S. And if the sulfur is gone, then also this process stops, which is also something that you can then say at the end of the day, okay, if I don't have any sulfur in my reservoir, then I do not care in any way, sure, because you have no source. And even if I have a source, you have to assess the potential for conversion, how high it is, and maybe then also come to a positive conclusion, which we did, because there is so little sulfur in there that it gets converted very, very fast, and then it is gone. And we never reached any critical H2S values. Last but not least, there is the question of how does the hydrogen move in the subsurface. I touched on that already. So there is this issue of gas mixing. We have two possibilities of mixing, one being diffusion and the other being mechanical dispersion. We found rather early that the diffusion is negligible in the subsurface because within the pore space, the hydrogen is not moving very fast. According to simulation, it is, but in reality, we haven't seen that the diffusion really makes a difference, at least if you see, if you have a look at our well tests. Mechanical dispersion, on the other hand, so the mixing, the actual mechanical mixing in the reservoir does happen, but there we just have now the information from the gas mixtures that we injected. We're not yet there with 100% of hydrogen. But from what we see from laboratory experiments, there should actually be not so much mixing. So there is a transition zone in between the hydrogen and the natural gas. but it's not a very pronounced one. So we should also be safe on that side. Still, there will be some hydrogen left in the reservoir. This is a physical process, and this is why I'm saying here physical trapping. And this is because you will exchange in your reservoir some of the gas that is in there, so some of the natural gas with hydrogen, in order to again arrive at a physical equilibrium. And one of the results from the USS 2030 project will be to get an assumption of how much of the hydrogen might be trapped in the reservoir. But at the end of the day, if you know this value, then you can price it in via CapEx, and then it's not a big deal. It's not very different to an aquifer storage, where you also price in that some of the cushion gas that you inject will not be recoverable. With that, we're already at the reservoir, and I see I have overextended my time, so I need to be a bit more quickly. Just a few numbers about the reservoir. So working gas volume is 1.2 million cubic meters of hydrogen that will be injected and withdrawn. We're currently at the in the injection phase that will be finished until the end of the year, and then we start withdrawing. I want to mention that the hydrogen is not just vented or mixed to the natural gas, but we have built the hydrogen CHP, where we generate heat and power for one of our commercial storages. The well, I want to mention that quickly, was tested before we injected hydrogen on its integrity, and it will also be tested again after the withdrawal of the hydrogen. I just want to mention that we do regular gas testing in both of the annuli, so between casing and tubing, as well as between casing and deformation, to find whether or not hydrogen does migrate through this annuli to the surface. Until now, we haven't measured any hydrogen in those annuli. The injection of the cushion gas, there was nothing special there except for a bit of decrease in temperature, which is natural because we're injecting cold gas. And so I come to something very important, the first withdrawal, because we did a test withdrawal already. And so we took out 10% of the until then injected volume. This was to test the whole facility and also the CHP. And during this withdrawal, we saw, as you see it written here, no mixing effect. So very pure hydrogen came out of the subsurface. We saw no H2S, which is actually the more important point for me, because the mixing I wouldn't have expected anyway, because we just took out 10%. So the mixing and the transition will come later. But the H2S, if there was some, we would have seen that early on. And as there was no H2S, in the gas stream as well as in the reservoir brine, we're actually very happy that it shows that the results from the lab saying, okay, if there is nothing to react with, then nothing does react, seem to also apply to the reservoir. But let's see, we have the big withdrawal phase will come in January, and maybe then we learn some more. And with that, I'll skip ahead to my final slide, which is the follow-up project, which is the EuroH2 stars. This project will support further 4 storage cycles to really get long-term experience with the reservoir and also long-term experience with hydrogen storage. Furthermore, we in this project will establish several replicators throughout Europe with one additional pilot that will be established until the end of the project. So we then not only have information from one reservoir, but from 2 reservoirs being injected and withdrawn with hydrogen. So we get actually a lot of data that will then help, and this is the final more or less result that will come out of this EuroH2 stars project, a basic engineering and basic design, let's call it a blueprint, how a future hydrogen storage facility, both in the subsurface as well as at the surface, could look like, and how we could apply such a storage system in the future energy system. I know I was a bit quick at the end, but yeah, as I said, that's like 10 years of research stuffed into 15 minutes. It's a bit difficult, so I apologize for being a bit longer than necessary, and thank you very much, and I hope there will be some questions in the end. Thank you.
Thank you very much for this very interesting talk, and for giving us an insight about the tremendous work that has been done already and your ways forward. We will take maybe one short question to this presentation. If anyone
Sure, go
has
ahead.
one, please speak up. Send your or raise your hand.
Oh, my video is working again. Yay.
I have one. Yes. I have one short question. This second pilot site that you mentioned, where will this be located? Is this already fixed or is it still in discussion?
It is planned to be in Hungary in the Pannonian Basin.
All right.
Operated by the company Hungarian Gas Storage. I don't know if one of them is here today. I haven't looked at all the people here, so maybe someone is here, then they can say a bit more about it.
Mm-hmm. Thank you very much. So I don't see any further questions now or raised hands, so I suggest we proceed with the next presentation. And I wrote in the chat that the test alarm ended at TNO, so I hope, Remco, that you're ready to go.
Yeah, no, I am. I'll share my screen again, and apologies for this interruption. It was announced 10 minutes before the start of this meeting, and then it went off, and I thought, oh, okay, we're in the clear, and then it went off again anyway. So here we are again, and I think I'm sharing my screen again, right?
Yes, all good.
Okay, this is the slide that we had to stop. And I was talking about how much underground storage we will need in the future energy system, and that's something that Forschungszentrum and Julie studied. And why is it important? Of course, because we want to know what role there will be for not just storage in salt caverns, but also storage in gas fields and potentially even aquifers. And yeah, on the left here you see what we found, basically that between 80 and 270 terawatt hours of storage would be required in 2050, assuming certain demand and production projections, right? And a certain role for the storages that are to be built. And what we saw also is that about 2/3 of that capacity would have to be import reservoirs. And then when you look at more the injection and withdrawal capacities, you also see quite large injection and withdrawal capacities. Comparing the capacity amounts to Hard4Europe Alliance, for instance, which is an alliance of storage operators, there's quite a reasonable match between their numbers and ours, and so it looks like this is a pretty robust result. We'll need significant amounts of storage for hydrogen in the future, to support the emerging hydrogen value chain. Yeah, so then where do we actually store all that hydrogen? Well, of course, salt caverns was already mentioned, but this project focused more on storage potential in reservoirs, and there we, from the HyUSPRe side, decided to look at what we call the low-hanging fruit, which is actually to repurpose underground gas storages for hydrogen storage, and we looked at how much hydrogen could then be stored in these underground gas storages, and looked at this at country level and even at site level, and came to these amounts as portrayed here at country level, at least on the right. There's also a site level assessment, and the data for that are also available, for instance, via the HyUSPRe Hydrogen Storage Potential Atlas, and I have the link here on the bottom left here. We divided Europe into 4 regions, northwest, central, eastern, and southern. And then you see here in the rose diagram, let me see if I can point here. In the rose diagram here, you see the division of the capacity over the different countries. So that is something that can be looked at in the deliverables. We use different methods for converting the capacity for gas storage to hydrogen storage. Of course, the well-known energy density-based conversion factor of 0.25. That basically, so hydrogen has 1/3 the energy density of natural gas, and it also has a different compressibility. So in all, that makes a difference just physically of 0.25 in conversion factor. So that means that only 1/4 of the storage capacity for natural gas would then be possible for hydrogen in the site. We also looked at other methodologies and for natural gas storage, applied known engineering, reservoir engineering methods like IPR VLP or nodal analysis to look at how you could actually improve the performance for the capacity for hydrogen storage of underground gas storages. And in the end, we came to some other relationships here, empirical and heuristic, that can be applied to convert from natural gas to hydrogen. This is all reported in deliverables 1.3 and 1.5, which are available on the HyUSPRe website. This is just a screenshot of the atlas, the HyUSPRe storage potential atlas, and it gives you an idea on the right also of the data that's available for every site. So would stimulate you to visit the storage potential atlas if you're interested in such data. Yeah, and then also the 2050 vision. So how could the future hydrogen storage infrastructure in combination with transport look like? On the left here, this is a figure from the roadmap, from the HyUSPRe roadmap that basically shows the cluster level capacities of a future hydrogen storage infrastructure and how it connects to transport with the yellow lines for the European Hydrogen Backbone initiative. We basically use those data from them. And on the right here is a figure from HyStories. I think Ceri, Vincent will touch upon that later. So on the left is basically the existing potential in underground gas storages when converted to hydrogen storage, and on the right is additional potential in new reservoirs, new fields that, if also used, could provide additional capacity to meet demand. So that's essentially what this slide is portraying. Then a bit more on the experimental work that we did and what did we learn from that. So also, yeah, in a way, preparing for a future pilot or a demonstration in countries in Europe like the one that has been and is being and will be done by RAK and partners in Austria. So more on the geo and biochemical reactions with hydrogen. We did a lot of work, both TNO and Edinburgh University did that, and that's basically published, and then Wageningen University, apologies, for instance, on microbiology, a literature review on the window of viability of different metabolisms relevant for hydrogen storage, where it's clear that temperature, salinity, and nutrient availability are very constraining factors to growth of these microbes. We did that, or Wageningen did experiments performed on samples of partner sites, where they observed that especially sulfate producers that produce H2S indeed, consume hydrogen and produce H2S, can at least also thrive at temperatures above 65 degrees and 2 molar sodium chloride, or equivalent sort of a measure for salinity, which is somewhat higher than what was previously known. So in that sense, that you could say is a new result. Then we also looked at the risk of hydrogen generation from the reaction of hydrogen with pyrite in reservoirs. It's clear that some reservoirs have pyrite, amounts of pyrite in various amounts. And what we found there is that this reaction actually happens quite fast, especially at temperatures, let's say at 100 degrees or above, but also below 100 degrees, the reaction occurs. In the meantime, we find that even at 80 degrees, there is conclusive evidence that the reaction occurs, although slower. So basically, it's highly temperature dependent. Lower temperatures slow the reaction down. There's also an impact of pressure of hydrogen pressure. Higher hydrogen pressure seems to promote somewhat the reaction, and this really calls for site-specific analysis when using planning to use a site or reservoir, conduct a site-specific geochemical modeling study, for instance, using parameterizations that are based on this data. And then finally, more on mineral reaction gates in general, we published a database, and we also looked at potential pore space reduction and geomechanical changes in build rocks from hydrogen brine mineral interactions. So plenty of results there. On hydrogen flow behavior in reservoirs, already mentioned by Markus in the previous presentation, we actually try to measure with experimental setups, or actually Clausthal University did that, molecular diffusion and also mechanical dispersion. And we also reviewed the state of the art of hydrogen flow porous media. These reports are also available on the website. So quite valuable new data that can help to inform numerical models, reservoir simulation models, to be able to actually simulate flow through reservoirs, and also history match with data like that come out of the project of RAK. The durability of wells and rocks, also quite some work done, in particular by TNO this time, looking at what's currently available in terms of practices and experimental data for well and rock materials and the cyclic hydrogen injection and withdrawal. Of course, the well connecting the subsurface reservoir with the above ground facilities, quite a vital component of the entire system, and also known to be known for its risks in actually causing leakage. So that's why there should be quite some focus on actually doing experimental work and also understanding what the additional risks are for now using well materials and components for natural gas versus for hydrogen versus natural gas. We looked at well cements that are currently used in wells, and basically did experimental experiments with that. And what we found is basically that there is a quite limited effect of hydrogen compared to nitrogen. We did not really observe changes in cement properties at the investigated conditions, which are actually representative of hydrogen storage conditions. Also on experiments on reservoir cap rock pairs, looking at changes in fluid flow and mechanical properties of the rocks under cyclic loading, we did not really find major effects of hydrogen exposure for the investigated conditions. There is some different behavior of sandstones exposed to nitrogen versus hydrogen. We particularly observed changes in stiffness, which actually the rocks becoming stiffer with the nitrogen than the hydrogen. For cap rock, this was a bit more pronounced. It's a bit unclear yet what that means for hydrogen storage, but I don't think we are particularly concerned about it. And then finally, more on scaled down well systems, testing the effects of hydrogen injection and withdrawal. Also, no major effects on sensor injectivity and productivity or injectivity of scaled down well systems. There was some response of sandstone pressure to well pressure cycling. It changes significantly if casing is hydraulically connected to sandstone. So, for instance, well, there are full perforations or fractured cement seed, then there are some changes. Maybe finally, just to wrap up, as I said, all the deliverables are available on the HyUSPRe website, 52 in total. We also organized 5 external webinars and published newsletters, and organized the final event in the Netherlands in June. The links are there on the slide. We can share this slide deck with the audience later. I think I should leave it at that. Thanks a lot for your attention, and apologies for the disruption.
Thank you very much, Remco. No problem. That was not you to set up the alarm. So thank you very much for giving us a very good overview of the different methods that you worked with to also determine or estimate the potentials in Europe and the experimental work that you did. Is there one short question from the audience to Remco's presentation? Then please raise your hand or post it in the chat. Very quiet audience so far.
Can you hear me, Cornelia?
Yes, I can.
Yeah, maybe a question to Remco. I will certainly raise it also to Markus. But Remco, the project emphasizes reuse of underground gas storage sites that are already existing. Though being a low-hanging fruit option, what would be for you the best arguments to still opt for, let's say, undeveloped gas fields, or let's say those that are not UGS deployed?
Yeah, that's a good question, sir. Yeah, one reason could be that the timing of I mean, of course, we expect natural gas to decline in use while hydrogen is emerging, right? Of course, we expect then that more and more gas storage is no longer needed, and that basically means that these underground gas storages would become available for hydrogen. The ramp down rate of underground gas storages versus the ramp up rate of hydrogen storage need, of course, should somehow match. If that is not the case, then of course we will have to look for additional capacity. That is one reason. Yeah, and another reason could be that yeah, the location of underground gas storages might not be ideal for hydrogen storage. There could be a difference because of production and demand balance requiring storage at a different location, right? So in that case, you would need an additional site. Let's say it like that. Yeah, just a few reasons and of course, but I think for sandstones, I would not immediately expect it, but of course it is conceivable that some of these underground gas storage reservoirs are, for whatever reason, not reusable for hydrogen, and that's that there is a possibility there potentially for the somewhat for the somewhat shallower depth reservoirs, maybe with the lower temperature, for instance, microbiology can have an impact. We think it's mitigatable, right? So not directly a concern there. But yeah, those could be considerations. Let's say like that.
And if I might add one more point, being if you're speaking about performance, now the classic natural gas storage is a long-term seasonal storage with just one injection and one withdrawal cycle per year. If I now up the game and say, okay, I need a second cycle or even a third cycle, this means significant changes in the surface facilities, and significant changes in surface facilities go hand in hand with build it anew. So that could also be a reason why you just switch to another reservoir that is not yet storage, because it's easier to build a new storage facility than to replace an old one.
Thank you, Markus, for this addition. And yeah, that's a good reason indeed as well. Okay.
Thank you. And then we come to our last talk given by Ceri Vincent. She's a geophysicist at the British Geological Survey, an expert on geological storage, and she will tell us on the HyStories project, that was already mentioned here as well, another EU project, and we are excited what you will tell us about it, Ceri.
Thank you. I'm hoping you can see my screen now.
Yes, not in presentation mode yet, but now perfect.
Okay, excellent. All right, with everybody else's technical challenges, I was getting worried about my turn. So I'd like to talk about the HyStories project. Thank you for inviting me to share some of the results. I'm going to focus in on work package 1, which produced a database of produced a database of storage opportunities for hydrogen in aquifers and depleted fields. You can see the website at the bottom, and all of the items should be available. So overall, the HyStories project looked at geological storage of hydrogen in the subsurface. It was kind of fun because when we started, there were no pilot projects mentioned for pure storage of pure hydrogen, and by the time we got to the end of it, I think there was something like 6. So it really just showed how fast things were changing in the field of geological storage. So the HyStories project, in work package 1, we looked at a pan-European database of potential opportunities that could be interesting to investigate and develop. We also looked at insights on mobility geochemistry and how much hydrogen we might be able to store in the sites identified in work package 1 as part of work package 2. We undertook microbiological test programs using samples from natural gas storage sites. We looked at materials for long-lasting surface equipment. We considered what storage demand might look like and how it might develop into a pan-European network. We considered if the regulatory framework was mature and looked at societal environmental impact studies. We also did some work on site development cost estimates and potential ranking of sites that were identified in as a pan-European in our pan-European database, and we did some further economic analysis on the case studies, and we shared all this as part of what could look like a plan for the EU. So I'm going to focus on work package 1. This was led by CO2 GeoNet, or by VGS on behalf of CO2 GeoNet. So the aim was to produce a European database and a geographic information system to show geological storage of hydrogen in porous media in Europe. So we collated publicly available data on where geological storage might be possible. And I think what's really important to note is that it was publicly available data. So we know that there's more data available, and we think the Net Zero Industry Act will release even more data that could be of benefit to studying the subsurface and understanding what the opportunities are. So it's really important to note that an absence of identified potential by HyStories does not mean an absence of geological potential. It may well just mean that we don't know enough yet to make a sensible comment. So the database then fed into the work on modelling capacity and support to the work on geochemical and microbiological work in HyStories. So the aim of the database was to highlight regions and sites that might be suitable. It produced a comprehensive database with a broad coverage of almost the whole of Europe. It advances the level of knowledge for hydrogen storage in Europe by making the latest relevant geological data available and including hydrogen-specific criteria in the database to support geochemical and microbiological assessments. And the aim was to produce more accurate assessments of the future potential for green hydrogen storage in Europe. So because the data that's available is very variable, we felt that we would follow the model used in previous geological storage databases. So we have a 3-tier database. So we look for a storage formation, which basically is a rock at a suitable depth with good porosity and permeability and some kind of cap rock over the top. We then start looking for where does it look most promising? And that would allow us storage units. And finally, where could we identify geological closures or traps? The reason that we do this is to take on board the heterogeneity of the data availability. And sometimes the data is not there, or sometimes it's confidential. So sometimes we would use a storage unit where, for example, we weren't allowed to share the outlines of the oil or gas fields. So as I said, things are changing now with the Net Zero Industry Act, and I think that's going to be very exciting. But at the time that we built the HyStories database, there was some limits on the data that was available. And it's also worth noting, as always, geological interpretation is interpretation. So where I might see a promising trap, you might not. And it's kind of really important to remember that geology is very heterogeneous. The way that we interpret it isn't always uniform, and that's why we need experts in the field. And in my experience, this is why geologists like to talk about the problems that we've run into when we're doing subsurface interpretation, because we know that every single site is unique. You can't sort of take one site and then just say, oh, that'll be exactly the same over here, because we know how geology varies in the subsurface. So what data did we collect? We collected basic geological data such as depth, area, thickness, permeability, porosity, lithology of potential storage formations, units and traps. In the traps, we also tried to collect more detailed data that would help with the modelling, so pressure, temperature, net to gross, environmental deposition, seismic and well data availability. As part of the hydrogen specific, we looked at the geochemistry, so we were interested in iron, sulfates or sulfides, CO2, and the fluid that was already in the potential trap. Of course, we're very interested in leakage risks, cap rock faults, depth to the top of the potential trap. And we're also interested in operational information, which could tell you about whether the storage site might be ready soon, what you would need in order to develop that for hydrogen storage. So in terms of data availability, it's worth noting that there was a lot more data available about hydrocarbon fields. We're not surprised by this. We know that aquifers to this point have not really been an economic proposition, so it's quite rare to find good data. However, we did note that in the countries where there's been more exploration for hydrocarbons, you did tend to get more data in terms of seismic and wells and general information about the subsurface. So we looked for as much data as we could find in the public domain, and we tried to collect this. And you will notice on the left, we have hydrocarbon storage data availability. It was better than the picture on the right, which shows you the data that we had available for saline aquifers. So sufficient data were available to identify geological traps in 20 of the 22 countries assessed by HyStories. There was significantly more data available for hydrocarbon fields and fewer data for saline aquifers. It's also worth noting that sometimes if you wanted to get the well logs or the seismic data, it might not always be available for free, or you might be able to access the data but not allowed to publish it. So there's still some issues around confidentiality and data availability and who owns and holds the data. So in some countries like the UK, the data is about hydrocarbon fields is released after an embargo period, whereas in other countries in Europe, sometimes that data is held confidential, basically in perpetuity. But as I said, we will see what happens with the Net Zero Industry Act. There's going to be a huge amount of data for us all to look at. So what we wanted to do was produce something that made it easy to see where the opportunities were. And so we produced an online data viewer. This is public and freely available to have a look at the data to see what we found. I'm going to be bold and hope that yes, the video is playing. I hope that you can see it. So you can see on the left, we have the information about the HyStories and what the database has got in it. From the database, you can select the countries that you're interested in. You can switch off the layers whether you want to look at them or not at the time. So in that case, you can see I was switching off the salt layers that SMRI very kindly provided to us. You'll see along the very bottom of the screen that we have the 3 layers in the database. We have the traps table, the storage units, and the formations. And you'll see that from the list of traps, you can select a single field that you're interested in, and you can scroll through to find all of the information about that trap, ranging from porosity to permeability to whether there's the availability of seismic and other data. And you can do this on a country by country basis. So in terms of the database results, so geodata is key in making strategic decisions on the role of the subsurface. So having access to that data and the knowledge on how to process, manage and manipulate the data has an important impact on the capacity for strategic decision making. Where geological data are available, it's possible to identify opportunities where the subsurface could play a role in meeting climate targets. And the wealth of data collected during the HyStories project indicates there is significant potential for geological storage of hydrogen in depleted hydrocarbon fields and saline aquifers across Europe. So where we did have data, we could find traps. All of the countries, with the exception of Estonia, were able to identify formations and storage units with potential for hydrogen storage. So the data that was available was variable, but everywhere except for Estonia, we believed that there could be opportunities that were worth investigating. The storage opportunities are not evenly distributed, and they will require varying amounts of effort to realise in terms of going from the theoretical storage opportunities that we've highlighted to an actual functioning site. In terms of the next steps, so the traps identified through HyStories require further assessment to confirm their suitability, which would mean acquiring detailed data, site-specific investigation and business cases. And additional data collection could be undertaken in a new project to improve the pan-European understanding of storage opportunities, which would mean additional resource to purchase, interpret seismic and well data, and new data collection, especially to better understand opportunities offered by saline aquifers. So in summary, HyStories Work Package 1 generated a comprehensive cross-border database with potential opportunities for geological storage of hydrogen. Public availability varies between countries and for different trap types. An absence of identified traps does not necessarily indicate an absence of storage potential. So the wealth of data does indicate there is significant potential for geological storage of hydrogen. Storage opportunities are not evenly distributed though. And the traps identified require further investigation to confirm site-specific suitability. Development time will vary. And with that, I'd just like to thank the rest of the HyStories project consortium, and thanks to HyStories Work Package 1 and in particular GeoStock, who led the project and also undertook the capacity assessment as part of the Work Package 1 database that you saw. Thank you.
Thank you very much, Ceri, for this interesting talk and highlighting the importance of data, as I'm sure we are all aware of how difficult it is to get data. And I see some gaps in the map where data is still very much needed so that we can proceed with the good use of building hydrogen storage. So now for the discussion, I want to give the moderation over to Serge van Kessel, another expert on energy storage from TNO. Please go ahead, Serge. Thank you.
Thank you, Cornelia, for handing over. And I want to thank the speakers all for great talks on this topic. And I think it's also very important information that we have to take into account for the Geological Surveys for Europe project. So, and everyone online within the GSU project, of course, I invite you to also raise your questions, because it's also where we need that information, and it is our opportunity to ask to the speakers. Maybe to start with a question to Ceri, because you were also the last to speak. You used the CO2 stop database, let's say, as a kind of a starting point, and you went through, let's say, that database structure to also identify hydrogen storage traps. Now, that has given, let's say, a very comprehensive view, I must say, and also a very nice viewer where we can explore potential in Europe. What did you actually also learn maybe back on the storage of CO2? Did this give you also new insights on the capacities for CO2 storage in Europe?
So it was actually very interesting to think about how many uses of the subsurface that we have that all rely on these data. So through the GSEU project, we look at geothermal, CO2 storage, heat storage, hydrogen storage, gas storage. We think about all of these uses, and so many of them all need the same data. They need the good reservoir, they need the seal, and they need to know where it is, how much space might be available, and if they can use it. So I think that the database, and one of the reasons why we kept a lot of the CO2 storage parameters in there, was to make sure that the database could be used for future projects, so that we could just keep using and enhancing this database and developing it to suit what we need for future use and a holistic look at the subsurface. And in terms of CO2 storage, I did look at this first and I thought, could there be a competition here? And then I thought, well, actually, probably not, because hydrogen and natural gas are both looking for something close to the people who are going to use the hydrogen or the gas. So they want something onshore. It could be smaller because it's an economic opportunity for hydrogen and gas. So you're not kind of looking for the gigaton scale that you might be for CO2. So for CO2 storage, it was very interesting to think about, to compare the two. So for CO2 storage, we want to be offshore, probably. We want to be something big, something we use once. We don't want it back. Whereas when we start talking hydrogen, it needs to be kind of small, responsive, onshore, and we definitely want something good quality back out of the subsurface. So there was a lot of learning, I think, between hydrogen and CO2, and there's things where we have something in common and things where what we need differs. And I think that was really useful and interesting to explore.
Thank you very much. It's a nice view here also on what kind of information can be provided, and maybe over to Markus as an operator, and now having let's say a pilot or demo scale project. Of course, you must be thinking about what's next to scale up, and what would for you be most important to know to make decisions about scaling up? What kind of information would you need to make such a decision? And maybe you should unmute. I think.
This is a good idea. Well, the question is very good and actually very complicated indeed. I mean, what would we need to further scale up? Basically, the knowledge of whether what we now did in just one reservoir, how relevant is it for other reservoirs? I heard it mentioned today that every reservoir is unique, and I fully support that. Still, there are synergies. There need to be some synergies, and so to really go forward a step and also to apply the system that we now test in this one reservoir, there need to be further pilots. Because only if I have tested this system and I'm speaking purely about the subsurface, because I think that the surface facility will more or less look the same around the world. It will depend on what is needed, which qualities are needed, but basically those components are there. But the subsurface is the unknown is the wrong word, because we know a lot already, but we know not enough to say, okay, I have tested now all these things in this one reservoir, and in the next reservoir it will be completely the same. So the question is, can I say it is the same in the same geological setting, or can I say it is the same in the same mineralogical setting? So this question needs to be answered in order to really roll out and scale up to another level. Because if I have to really test each and every reservoir around the world where I want to do hydrogen storage, this can't be feasible. We need a way to streamline this, to get this faster, to see, okay, these things I can use already, to end up with a economic preparation plan. Let's call it like that. And I mean, this is where EU H2Stars is going to. This is the plan here, to really have enough information available to say, okay, hey, do you want to build in this reservoir your new hydrogen storage? We can already provide you with this information. You can use that. And there are these 3, 4, whatever questions that you still need to answer, and then you're ready to go.
Thank you very much. Nice and also comprehensive answer on this question. And maybe also go over to Remco now. Yeah, you have been doing also some assessments within HyUSPRe and developing an atlas on the potential, especially for underground gas storage sites that can be repurposed for the use of H2 storage. What would be for you, let's say, may be the main barrier to estimate, let's say, and mature the potential for H2 storage sites? So if you have, let's say, that atlas of locations, what are the main barriers to get to maturation of these sites?
That's a good question indeed. Of course, I mean, every site serves not just a system need, but also a local need. So it's important to look at the site in the system and look at what the local and regional demand and supply do, and how that signal that storage need that emerges, how that fits with the site characteristics that are there, right? And indeed also Markus rightly mentioned that yeah, indeed, when it comes to capacity and performance requirements, then there is definitely a difference to be expected between hydrogen storage and natural gas. Hydrogen only containing 1/3 of the energy content of natural gas, of course. It may not be so easy to reuse either the wells or the reservoir. So that will be a step forward to get a better perspective for more sites at least. What would be the future profile for the use, right? So that is one aspect. Something else is perhaps so the need for cushion gas. So of course, the underground gas storage sites contain natural gas, right? If we want to convert the sites to hydrogen storage, then what do we do with the cushion gas? Do we leave a certain amount of natural gas in the reservoir and then use that as cushion gas, or do we want to empty the underground gas storage further to replace also some of that natural gas with hydrogen cushion gas, which is, of course, it has a certain impact from an economic perspective in terms of capex on the front end, but then later on might reduce the need for additional separation of natural gas from hydrogen. This is definitely also a topic for research and also actual piloting and demonstration, right? To learn from actual sites what the mixing behavior is between natural gas and hydrogen, and how that impacts above ground facility requirements, and also be able to predict how that will basically progress when using the site, right? So when you are able to predict better how much natural gas is mixed with hydrogen when it is withdrawn, and you can also, and for how long, and what happens to that over time, you can better tune your above ground facilities to that.
Thank you very much. One question for, and which maybe builds on this topic for Ceri. In GSEU, we're talking about implementing these storage readiness levels. And if you look at the pan-European product that we can establish, and let's say take the HyStories project, what is, let's say, the best achievable storage readiness level that you can achieve on a pan-European product? I hope you can fit this with a question.
Thank you. So, I mean, the storage readiness levels, and the paper is Akhurst et al. 2021 for CO2 storage site development readiness levels. And the aim was to think about, was basically to find a way of communicating all the work that's left to do. So this ranges from your first look at storage readiness level 1, where you just say, yes, there's some rocks at depth, all the way up to storage readiness level 9, where you're actually injecting CO2. And you say that, yes, I've now proven this because I'm actually injecting. I know this site will accept CO2 injection. So in terms of storage readiness levels, for a pan-European product, you're really only looking at up to storage readiness level 3. And this is where we start to look at the potential opportunities, and we screen them based on technical, economic properties. So that is probably as high as you will get for a pan-European project. After that, it tends to go to national products, where you start to pick out the most promising opportunities, and you move up into storage level 4. And that's probably as high as we would go for a research project. After that, it starts to require much more detailed characterizations. You might start tipping towards into storage readiness level 5, which means you start to do a really detailed site characterization. And after that, you're really into the purview of companies that are going to develop individual sites. I still feel that the work that we do as researchers to get us to that pre-commercial level is incredibly valuable and useful. And in the UK and Norway and the Netherlands, we all see there's been development of sites by researchers for many years before commercial companies are willing to pick this up. In Denmark and the UK and Norway, we've all run kind of storage licensing rounds. And a lot of this is based on lower storage readiness level work that's been done using existing seismic and well data to say, here's an opportunity, it's worth looking at. And the commercial companies with their own economic and risk models will then look at those opportunities, pick out the ones that they really want, and take those forwards, hopefully all the way up to storage readiness level 9, where they're actually injecting. Thanks.
Thank you very much. Maybe that also brings me to a question to Markus. If you look at pan-European products like the HyStories and the HyUSPRe maps, suppose they are online, and in GSEU we want to integrate that information, build forward on that, and make it improve the information on the possibilities for hydrogen storage and maybe also CO2, etc. What would you expect mostly from a product as a pan-European product like the HyStories map, for example, as an operator? How will it help you make choices and make decisions? What is important for you to find in that kind of product? How would you use it?
This is a very good question. I never thought about that. I mean, I'd take a different take on this actually. So as an operator, I'm mostly focused on the region that I'm operating in. So I probably have a rather good idea about the subsurface and what is going on there and what I can expect. However, if we're speaking about developing a storage project, this is nothing where RAK or Uniper or whoever just comes and says, okay, I'll build a storage there. There is always a process behind that, and there is always a customer behind that, being it an investor, being it a joint venture partner, something like that. And I guess actually that for those people who are not aware of, okay, what in this specific geological region is going on, this is actually something they will need, because from there they can quickly assess, and this is what then is needed. Okay, what volumes do I have to expect there? what issues do I have to expect there, what research is already there. So is there already CO2 or hydrogen specific research done in this region, or is it completely a virgin field, a virgin geological area? And I think those informations would actually be very important, again, then also for the operator, because if I can say, yeah, look it up quickly, there is this map or this product in the internet, and you can get the first assessment and the first idea, that also means then that you have some kind of positive advertisement or negative advertisement, in the worst case, for a special region. And it will also help get data for such a product, because then I, as an operator or someone who owns natural gas fields or salt, a permit for salt, might then actually be more interested into publishing data from what he has already done for such products, making them more, giving them more information that can then be provided.
That triggers also another question, because what I hear you say is knowing what kind of information is there and what kind of studies have been done is maybe most important for you.